Okay, so we were talking about definitions yesterday. We got all these. We got magnetic flux, flux density, permeability, reluctance, retentivity, residual magnetism are the ones I threw out. And now we'll talk about material properties. All right, soft irons. Soft. Well, if you get hit in the head, there is no such thing as a soft iron. But that is to say low carbon steel. Low. And you would think that, well, it's an aircraft. Why would you ever use a low carbon steel? Why would you use soft stuff? And why not go for the best? Well, because sometimes you want things that are a little bit more bendable rather than breaking. So the harder it gets... Okay, so back to what I was saying. Why would you want to make something soft? Well, I said because you want it to be a little more bendable. The harder something becomes, the more brittle it becomes. Yes, it's very hard. Like a crankshaft, you want those journals that it's going around inside the bearings to be hard because you don't want it to wear, right? But you want it to be, some parts, other things be bendable. Let's take a rocker arm. It's a thing where it opens up the valve. So you got a rod pushes on the back and it has a fulcrum in the middle and it pushes down on the valve stem, right? So that particular engine part is got hard in some spots and soft in the other. So the very foot that makes contact and wipes across the valve, which has stellite on it, which is a really hard material, it's a hardened foot on a hardened piece. But the rest of it is not. It's actually quite soft so that it doesn't break and it will bend first. So you have to think about what it is you're working on and is it a hard thing or a soft thing, because you have to understand these properties of magnetism in order to properly do what you're doing. So soft irons, low carbon steel, they're going to have high permeability. Easily magnetized. So that means it's going to have what for residual magnetism? Okay, low residual magnetism. We have, I'm going to move it over. You're going to be okay?
Yes, sir.
Okay. I'm not going to freak on me. We have the hard irons. Hard irons, which would be
for residual magnetism. Is that kind of the same thing?
What's that?
Is retentivity the same as the residual magnetism?
Yes, absolutely. I could have put that. Where my high carbon steel. And that is low permeability. So is it easily magnetized or hard? Hard to magnetize. Hard to magnetize, which means retentivity is going to be low or high? Okay. Which means the retentivity is going to be, wow, we said that, high. Retentivity.
So if you were to magnetize something that's, a hard iron, and you don't demagnetize, would it stay magnetized forever? Like, does it wear?
Well, we'll talk about magnetism, but yes, it will stay magnetized. And the problem with something staying magnetized is it tends to attract iron filings to it, which then are going to stick to it and cause wear. I guess some people could argue that if you have a large magnetized ball up front of the airplane, it could actually affect your compass and such, but I'm more concerned with the fact that it's going to attract iron filings. I want the wear of the engine. We're breaking in an engine, and which means that the cylinder walls and rings are wearing together, which creates a high iron content in the engine. I want that stuff to be picked up. Someone's stealing the car.
Check it.
Toyota truck.
That's probably,
So, to the girls' car.
That's Hector's baby.
No, not the black one.
Oh.
Thanks.
I was leaning over to grab it. It's an eraser.
All right, where was I? So rudely interrupted.
Breaking in a new engine.
So you get these iron filings. I want them to be carried off with the oil into the oil filter. Now I don't want to be sticking to the crankshaft and eating up the crankshaft. So I want to get rid of them. So it's really important to demagnetize these things. When, like I said, we will talk about demagnetizing, but in case I don't have this written down or a note, demagnetizing actually gets down to a point where you're supposed to store the crankshaft in an east-west, long pieces in an east-west, not north-south, because it'll start picking up magnetism from the earth and remagnetizing itself. So,
Wait, what?
yeah,
How long was
that is the
have to
truth.
be north to south?
I don't know. I never tried it. I never worried about it. That's
Wait, so say that again? So if it's magnetized,
if you demagnetize something and leave it laying for a long period of time in a northwest orientation, it will pick up magnetization from the earth.
That's north to south?
Yeah.
Flux going from the north to
Yes.
south, and then it's
What happened to Mythbusters? We need to solve this for you.
Well, what we could do is we could go right now. I could go get a crankshaft, demagnetize it, bring it over. We'll set it right there, and we'll just sit and watch it.
I like the sound of that.
That's the final test.
Because you got to test tomorrow, or not the day after tomorrow. So it doesn't matter to me. I get paid the same.
That's for lab hours.
Yeah, hysteresis. That's what you have. Hysteresis loop.
Only women get those.
A hysteresis loop.
Your wife's gonna hear that.
Let me see. Well, I thought I had. There we go. There's a picture of a hysteresis loop. All right. So we're going to talk about this hysteresis loop. And it's very important to when you're talking about the field of what we're doing, magnetic particle inspection. Slideshow from current slide. There we go. And I will talk about it a little bit and then write some stuff here. But just to kind of give you an idea what it's doing. So understanding a hysteresis loop helps you understand not only the magnetizing process and really how much amperage you should be going into something, but also how it is that it demagnetizes something. So if I told you to demagnetize something, if you magnetize it and then to demagnetize it, well, the idea is you want to scramble those little domains in there, right? And so if you just took that and you put it inside of an alternating current coil, and the coil and the alternating current's going back and forth, and you move it around in there, then in theory it should just scramble them and then be done. You can get rid of it, right? But then if I tell you, you can also demagnetize stuff with DC or step down current, you'd be like, well, why does that work, a step down current? Why is it, if you magnetize it at this and you magnetize it here, well, why does that demagnetize it? We already magnetized it here, and then you get this current that's lower. That shouldn't have any effect on it, right? But it does. So that's where this hysteresis loop comes in and sort of explains what's going on. So in this loop, you have this right here, this dotted line. And the dotted line is always thrown in there. They call that the virgin loop or the virgin something or another. But what it's representing is this spot right here is the point of zero flux density. So you can see up here a flux density up, flux density in the opposite position, which would be to say if I had a crankshaft and I had one of those little Gauss meters that, forget that not everybody's in there doing it.
Isn't that what we used on our...
Yeah, one of these little...
Magneto?
Yeah, the magneto. You guys did, okay, so the Gauss meter magneto, right? The north would make it swing one way and the south would make it swing the other way, right? Thanks, Eric. Okay, so, all right, so if we were to lay the crankshaft down, we'd bring up that Gauss meter and go, whoa, it's swinging real hard to the positive, right? But then we go to the very next crankshaft, do the same thing, and well, that one's going negative. See, one's got magnetism going one way and one's the other. So one's got a north at the head and the other one's got south at the head. Understand? So, but anyway, what I'm trying to say here, not eloquently, is that you have flux density going one way versus the other, and that's like the plus on the Gauss meter, and this is the negative in the Gauss meter. But 10 is 10, right? but it goes back and forth. So when we magnetize something, let's say I put, 5,000 amps through it. Well, it's not, there's a point where this part is only going to get so magnetized. It can't just continue to get more of a magnet. If all the domains are lined, it's done. It's saturated. They're all lined inside of there, and so you're done. And if you were done at 1,000 amps, giving it 2,000 isn't going to make it more of a magnet. 5,000 isn't going to make it more. So that's what saturation is. It's just to the point where that part has become 100% magnetized.
And that has to do with the material it's made out of.
Exactly. Okay. So now this is that saturation point. That's with the power on, the button on. It can't get any more magnetism. But as soon as I release the button and I'm no longer magnetizing it, it's going to roll down to retentivity. That's what's left. So that's the difference. And again, it's kind of cool because a lot of you have already done this. I'm trying to remember those that haven't. When you're putting the fluid on a part, there's two methods of doing it. One is called the residual, and the other one is called continuous flow, and the other one's residual. So in a continuous flow inspection, I take that fluid, so there's a fluid bath with these iron filing ends in there, and I will actually get the part very, very wet. And right at the point where I've got just covered in this fluid and it's dripping off, I'll stop the fluid and hit the power button, and boom, right? Give it a couple thousand amps or whatever I'm going to give it, charge it. And what happens is that fluid was really just it was running and pouring on it, and it's going to go to it any indication that it has. Okay, so that's the continuous method, meaning that the fluid was put on while the power was activated. Now, you can't leave the nozzle on because you could literally wash away an indication. You want it wet and flowing, but not out of the nozzle. Okay, so continuous flow. The other one is where we can just magnetize something and then go, okay, now I'm going to get the fluid and put it on. So on the first one, you're really looking at more of an inspection under the saturation level of its magnetization power. But the other one, where you magnetize it and then put the fluid on, you're looking at doing it under the retentivity power of the magnet. So you can see at one, it's a lot more powerful than the other. Now, some material, like these harder crankshafts or things that are hardened that have high retentivity, if the retentivity is way up here equal with saturation, then you got it made. You can keep doing it over and over and you don't have to apply the power, but that's not usually the case. It's usually retentivity is a little less than what saturation is. So anyway, we apply the power. We can apply the fluid at that point. We've done it at the saturation level. Remove the power, it pops down here to retentivity, and there it is, just hanging out at retentivity. So the up and down, again, is the flux density. Does you follow? So if I checked it with my little Gauss meter, we'll say it's 10 here at saturation, then release the power and it comes back down here. It's only 8 now. Follow? Okay. So we're sitting there at 8. Well, I want to get rid of it. C and F are the power, how much power it is. We could say that's 500 amps here, and we could say that's 500 amps there. I'm just making up something. And then this we could say is plus 10 on the Gauss meter, and this is plus 8 on the Gauss meter. Just, again, making up stuff. It's just all relative terms. So all right, so to get rid of that, to bring it down, if we then demagnetize it in the opposite way, then you're going to apply 500 amps, and it's going to saturate to this end. It's just upside down, what we're looking at. So it'd be minus 10 here, right? And then we release the power, and it goes back to minus 8 there. Follow? Then if I put 500 amps, we'll say positive, we'll say negative, positive 500 amps, so it's going to go. And so that's the hysteresis curve. And the reason why it's a curve and why this is important is because certain metals will look different. And understanding, let me see. I didn't make, let me see. I don't know if this one has it. One of my slides, I didn't think about it before, but it's actually got multiple hysteresis curves. It's like, I thought that would have been cool if I would have showed that. It just came to me.
But basically for like a soft iron.
Yeah. So I don't know. I don't want to spend all night looking for that. But let's think about that. That's a good exercise. What if I had to do a magnetizing force way out here to get the saturation? Would that be something that has more or less reluctance? More reluctance? Takes more power to get it to plus 10? Okay, so that would be a much fatter looking thing. And there, well, that's terrible. So, okay, so if it, you got
We
me.
get it.
This is one of those nights. So if it's much fatter, so is that going to be a more hard metal or a more soft metal?
Harder.
All right, you guys are getting it. Okay, so if it was much narrower, then that would be,
Soft.
I like that. Okay, so you did, I did okay. All right.
Once you started drawing on there and explaining that.
Yes, once I start randomly scribbling on something, it's like, what do you know? Yeah.
But
That's that alarm went
the
off,
re-
we got
like,
it.
the point of retentivity and saturation would probably be different though, right? Like how high up it is on the scale.
Damn
It's
you.
like you were saying, a hard metal, it might have more retentivity as opposed to soft.
Yeah, so we could actually make the whole curve different where the retentivity could be up here, so it really holds up a little bit more. But it could also be, it would come out this way because it's going to take more coercive force to get it to do that. So yeah, it just becomes a much fatter looking, not to body shame it, but things you got to worry about now as a teacher. All right. So
He's gonna report you to the dean later.
he was fat shaming the hysteresis loop. You wouldn't be the first one to turn me into the dean. Behavior of magnetism in a ferromagnetic material.
Look,
All right.
Make the world less fun.
The horizontal, the
God, I wish I was there for that.
horizontal stabilizer.
the horizontal axis H. You want me to write down everything I just talked about this hysteresis loop? All right. What? Everybody's afraid to say yes. Represents the magnetizing force. I'm just going to write it so sloppy you can't read it anyway. All right. I'm trying not to. I missed that. What? What did she? Oh, that's from you? I expected so much better. Give her this application. It's not. It's an NDT application so there. All right, the vertical axis. I missed what you said too.
Super betraying.
What did she say?
She said it's always been sloppy.
It has, huh? But it gets worse.
As the year goes on, we adapt to it. Yeah.
I'll try nice. You know, if you don't sit in the back, it's not so bad.
You just gotta adapt to it.
Yep.
It's like when you have a toddler and like the parents completely understand what the toddler's saying and you're like, I have no idea.
It's basically my writing for you guys. Something like that.
Yeah, we just know.
Almost made it through the whole semester.
She did, I know. All right. Flux density. Zach, wasn't it you who tried to write up here for me one
I
time?
did.
It
Looks just about the same.
it's-
It's not worse.
Okay. And then try to talk into the same time. The vertical axis, B, yes, represents the residual magnetism, that is flux density, after the magnetizing force is removed. After the magnetizing force is removed. You know, you guys did so well not making fun of me all semester.
That was your statement.
I still haven't said it.
Yes, it hurt my feelings, but fortunately for you, my feelings regenerate that at twice the speed of a normal person, so I will be over it soon. After a good cry on the way home, all will be fine.
We'll have this.
You're gonna be over before you grade our exams tomorrow, right?
Probably right after that. You know, I find the best way to make myself feel better is to make somebody else feel worse. So it's
You'll just tweak one of the grades just to.
okay. Magnetizing force is applied. That was the H plus going to the up direction to the saturation point, to the saturation. To the saturation point. And you know I really like you guys since I'm taking your abuse and I'm still writing because one class abused me and I shut this down and I just talked for the rest of the night and it was wonderful for me.
And they did a great job.
That's it.
I understand sarcasm when I hear it. The force is removed and the remaining magnetism and the remaining magnetism decreases to point B.
What is point B?
I'm going to pull it back up.
Vertical axis.
Oh.
Okay, so what I said so far is the horizontal axis H represents the magnetizing force. The vertical B represents residual magnetism, flux density, after the magnetizing force is removed. Actually, it's just flux density, period. I shouldn't say it's after it's removed. We could probably get rid of that. It is just flux density because it's up here right now with A, and it's going to drop down to B. So flux density, I'm going to change that. Pencil. No, I'm not. Left my stuff in my coat. All right. And then we said, so a magnetizing force is applied, H plus. So this is the H plus this way. So magnetizing force is applied to the saturation point. So we're going to add current, whatever it might be. And like I said before, it was 500 amps. I could have wrote 1,000. I could have wrote 2,000. Doesn't matter. So to this point here, which then gives me a saturation level up to here to A. Why they have to put L over here, I don't know. Okay, so A. The force is removed and the remaining magnetism decreases to point B right there. And then when the magnetizing force is applied in the opposite direction, the process is reversed in the opposite direction. Magnetizing force is applied C and the part reaches the saturation point D. When the force C is removed, the part has residual magnetism E. You gonna be okay over there? Is the chalupa kicking in or something?
Why did we try to hear it? He like spilled something and it was like, what the fuck are you doing?
Try to smell it. It was actually not good.
After you drink 3/4 of it.
When a magnetizing force is applied, applied APBL IED, applied in the opposite direction, the process is reversed. Process is reversed. And I don't think I need to write down the reversal of that process. It's the same thing, just me writing more. But now I can talk about demagnetizing. So 2 methods of, magnetizing. I said demagnetizing, but I meant magnetizing. All right, so 2 methods. Direct. Direct magnetism is when you actually run current directly through the part, like it's a wire. You are going to put many, many amps through the part,
Well, could you just go back a tad?
the TAD. Is that an industry term?
Yeah, right there.
All right,
Well,
direct.
that would be a headshot, right?
It is. Headshot could be something else entirely. Current is passed directly through the part. Also called a headshot. Or 2, indirect. This is where current passes through a coil. Current is passed through a coil that creates a magnetic field that is then induced into the part. Coil that creates a magnetic field this field passes through the part. All right, that's called a coil shot, if you will. So, in colloquial speak, headshot, headshot. This is coil shot. So quite literally, what I'm saying is you either put it in between the head and tail stock with these pads on it, copper pads, and the voltage or the amperage, voltage amperage comes right up through those pads, leaves one, goes through the part and out the other, and that's the complete path. Or you take a loop of wire and you just run it around in a big circle, and then you energize that, and that circle then creates magnetism within the circle, which transfers into the part and magnetizes the part. So you have direct or indirect. It's coil shot, headshot.
Kevin, with the coil wrapped around it, is that when they talk about demagnetizing it, you just unwind that coil?
Not really. Well, I'll get to D.
Okay.
Yeah.
Part's been throwing me off.
Okay, good. We'll get there. Let's see. Different types of current. So we have different magnetizing currents. Used to be you'd buy one of these machines and you told them up front what you wanted for a current. And you had a choice. You could have an AC current, an AC machine. So it stands for,
Alternating current.
it's like you guys have had electricity. I don't remember it. Did I? All right, we'll talk about alternating current a little bit. To kind of,
PTSD.
so in alternating current, you have alternating, you have direct current, right? And of course you have a few others in between there. What am I going to talk about? Yeah, there's a few others in there. AC, of course, then there's DC, then there's half wave DC, and then full wave. That should be AC. Half wave and then full wave. Okay, so our machine is either, you're going to select either AC or DC on it. When I was in the field, my machine was strictly AC, as were the older machines. You would have to have a completely separate machine, I believe. I've never seen the older ones that have both. The antique sitting in our entryway there was the old machine. That's strictly a DC machine. So the difference is with AC, and you think about it, wait a minute, that's alternating. I mean, is it really, doesn't it just kind of scramble? But it doesn't. It actually magnetizes using AC, and it's kind of cool. And what it does is, it's called a skin effect, is what happens with AC. And the best way to describe that with AC, the skin effect is all those lines of flux, they travel to the surface. And so in other words, trying to say that one, where it otherwise would be flux density through the whole part, that flux density wants to rise to the surface. So now you have more flux density along the surface. So given that the magnetism is not deep in the part, but very shallow, what kind of discontinuities will you find? Surface, and you'll find them very well because of the skin effect. Let's talk about DC then, where DC tends to go deeper. It's more, I don't want to say that it won't do the surface, because it certainly does. And I can prove that real easy. You guys have done the Ketos ring. You can see that it does it. But keep in mind, too, the Ketos is subsurface the way it is. So the DC is going to go deeper, and it's going to be much better at finding subsurface. All right, so the theory is, if you're a manufacturer of steel parts, what kind of defect would you expect from a brand new part? Why subsurface?
Inclusions in the forging process.
Yeah, inclusions in the forging process. These are gas pockets, or that's one of the bad things about the level 3s. You get to learn all of the different, a gas pocket, a pipe, a cold shunt. Come on. There's a million little names for these things, but you can get these, we'll just call them discontinuities, down deep. So if you check a new part and it's past the DC and the subsurface, and you put it in service, you're likely not going to get a subsurface problem with the steel part. You're likely going to get a surface problem. If you have a prop strike, it's not going to break down inside, it's going to break on the surface and go through. So the theory becomes, for manufacturing, DC is better, subsurface. For in-service parts, AC is going to be better, skin effect. You're going to see the cracks up on the surface much easier. So AC, due to skin effect.
And out in the field, you're not going to NDT a brand new product from a factory, are you?
No. I probably should have a few times. Due to skin effect, maximum lines of flux are produced on the surface. So AC works great for surface flaws. Surface flaws. Poor at detecting subsurface. Subsurface flaws. Okay, remember what the Ketos ring is?
Yeah.
I don't trust you.
Big round thing with the holes in it.
Big round thing with the holes in it. That's a technical term. There we go. Big old thing with the holes in it. And so you can see that there is no surface flaw on here. Number 1 is at 0.7 of a depth. Yeah, 0.7 of an inch. But it's not a surface flaw. So let me ask you, super guys, was this shot using DC or AC?
DC.
DC for sure.
Really?
Oh yeah. There's my first indication. Super sharp?
But didn't we see farther? We saw like 5, and then it got fuzzy.
5, then fuzzy. I'm going to bet this was DC, because you're picking up a pretty deep one. That's pretty deep right there. That's pretty deep. Usually with AC, and by usually I mean yes, this one will be really bright. This one is going to be fuzzy at about like that rate. About that rate. So I would take all these and move them down too. So you'll get a little fuzz here. This one's going to be pretty dim. That one you're going to probably be more imagining it than you are seeing it. And that one is just not going to really show up at all. Yeah.
I will confess that in a slow moment, Harry and I played with the Ketos reading today, and that's exactly what we saw with DC.
when we did AC, we saw the lines 1, 2,
Yeah.
the shallow ones.
Yeah.
But you couldn't see any more than that. But when we did DC,
It looks like this.
It looked like that.
Yeah,
You
so that's
saw
what I said.
like
This
7
is-
lines.
That's a DC right there. And Tobias agrees, so
And we did not drop the glucose ring in front.
you did not. Yes.
We really didn't.
Trust you a little bit.
Only dropped it a little. Really back there.
And then we did not use aluminum on the grinder either.
Oh, now I'm curious. Let me see.
What?
What?
Aluminum on the grinder? Hope not.
Signed up for grinder.
Oh my gosh.
Whoa, whoa.
Just wanted a price.
Expensive.
James.
Do you see a price up there?
665.
Where are you seeing that?
Right there. Remember?
Oh, there.
Oh, yeah.
Yeah, that's about what I expected. 665, 683. And the reason why I bring this up is because Michael just said, and we didn't drop it.
I know.
So, and the reason why is I bring this up is you put this on a bar. There it is. There it is. You put a bar through here. I don't have the picture, but it's on a bar, and then you put it in the headstock, and you push the little button, for those of you who haven't done it, down the floor, and the pneumatic ram goes, and it clamps it in there. And if you step on the foot pedal and open it up, this $650 part is going to fall on hard steel bed below it. There's 2 of them spaced about that far apart, so it'll put 2 nice big dents right in the middle of it. So if you do that, I'm going to ask you to buy me a new Ketos ring.
With this donation money.
Yeah. Like, well, that's okay. You can have this one. Can you bring me a new one? And then I'll get a call. Kevin, did you actually ask us? Okay. Produces best indications. Produces the best actual the indications because it causes the particles to dance around. Particles to, we'll say, dance. I don't know if it's like a line dance or whatever. They call that particle mobility.
I think line dance is perfect.
Particle mobility.
I'll get in the line.
It's true. Particle mobility.
All right, so all that's left to explain is, well, how does AC work then? Doesn't it scramble it? So the AC frequency at 60 hertz is higher than the hysteresis loop moves. That's a bad sentence, but higher than the, say, movement of the hysteresis loop. So in other words, its frequency is moving much faster than this hysteresis loop. So while it's kind of doing its thing, the hysteresis loop spreads out. That's why we go for a full half second instead of just a part of a second. So half of a second, AC is moving at 60 cycles per second, so it's going to move 30 times in that period of time. Then we do it twice. So it works. All right, the other one is DC current. DC works best for subsurface flaws. We'll leave it at that. Does not work well for surface discontinuities. Well, that's just being redundant. So,
Why does it not work as good?
because of the skin effect.
But so that doesn't produce the skin effect?
It does not. AC does. So that's why DC is best for the subsurface flaws.
subsurface? Like you would see a problem, like, I could imagine probably not in aircraft form, but.
I'm trying to figure out how to answer this, so maybe I'll just answer very honestly. When you're in the dark room and you're looking at all of these parts that you're looking at, and remember that it's a little different than in the classroom setting, because you're going to clean all of the entire engine, you're going to bring it in there, and you're going to spend the next 2 hours in there looking at a full engine. And there's a lot more stress that goes with it, because what's the consequence for you missing a crack in class?
You don't get a good grade.
That's not even an option. I'm still going to give you a really good grade. So it's a zero risk environment. So as you're doing it as a real tech, it's a high risk environment. For you to miss a crack could be to kill somebody. So you have that weighing on your shoulders, but at the same time, you're dealing, at least I was dealing direct with customers, knowing that to falsely reject a part could be not only very costly to the client, but also kill your reputation. As I was talking earlier about, if you have a reputation for red tagging parts that shouldn't be, you're not going to be in business very long, because the normal customer, I know this is what I would do. How's the saying go? If you're like me, and I know I am, or if you're like other people, and who isn't, if I took my engine in to be NDT'd, and mind you, not that it matters, but a lot of my work, I did a lot of work where I overhauled engines, and I did a lot of work where I prepped engines for people who wanted to do their own work. And so I would do all the disassemble, clean, inspect, repair, NDT, machine work, and give it to them in a stage ready to be assembled on their own. So if I were to red tag something that wasn't really worthy of being red tagged, especially a crankshaft, all they're going to do is take it and ship it to a different shop and get a second opinion, and they should. That's what I would do. Is it really cracked? And thankfully, I never had a time where it came back and said that, oh yeah, no, this is totally fine, which probably means I just missed a bunch of cracks, but just kidding. And so what was the question again?
I think it was more on these, like, is there ever a point where you're actually going to look for something subsurface?
Oh, that's right. So subsurface. So the honesty part was, you're training your eyes to look for a certain thing. There's certain things that are going to jump out at you, and you kind of, I guess, maybe you have a mental picture in your head what you're expecting to see. So you got to be careful with that confirmation bias. And so I'm looking at these things under an AC machine, and this line right there is not something that's going to catch my attention. Number one, because this line that you're seeing right there is produced by it's a 1-inch wide deal where somebody drilled a perfect hole and giving you a perfect line. If you get an occlusion or some sort of subsurface discontinuity that was there from the manufacturer, number one, you're finding a manufacturer defect, which is rare. But two, it's going to give you an indication that is not something that will probably catch your eye, because the rest of the part is not perfect like this. This is a perfect finish with a perfect indication. So, you're looking at these crankshafts, think about how the journals are all highly polished, and that's the only polished part. Next to it is not. It's a rough surface, right? And so you're looking at a rough surface, a polished surface, a rough, a polished. And it's just these subsurface indications aren't going to come out at you. It just isn't, especially on these rougher surfaces that I can see. So your eyes are going to pick up more on the more definitive surface lines. They jump out at you. I don't know, maybe that helps you, but I guess the truth is I wasn't looking for subsurface.
I get what you're saying.
Yeah. I mean, if I would have saw one, I would have been all about it. But I will tell you that, there have been times where I've seen just the faintest of things, and you know that it shouldn't be there. The weirdest crankshaft I've ever seen was that one today. I'll be honest with you, that was the strangest cracks.
Really?
Yeah, I've never seen anything that bizarre in my life. I would love to know where that came from. But so the hard part comes, you'd find something and you're like, well, now what is it? So, you'll take it outside, you'll look at it under a magnifying glass, you try and interpret it. Is it just a little dip in something that's catching the fluid? What's going on with that? Oh, it's break time, sorry. Then you cannot do anything that you don't have approval for. So, like in there, I took a little grinding disc and I polished it. That is a 100% illegal move. You can't do that. At the moment in real life that I did that, I'm condemning the crankshaft. You can't remove material from a crankshaft. So the best I could do, you're allowed to polish it. So I could use like some 320 grit paper, kind of rub it a little bit, which does kind of ruin your skin effects. You have to remagnetize it. I had, like I said, little rubber wheels that would just polish, and I would polish. And sometimes you start to polish a little crack, and boy, it really starts to open up. It's insane how it does it. Very few times that I see something like that and polish a little bit, and I'm like, oh, it just went away. I mean, sometimes it does. Sometimes it starts getting bigger when it gets bigger.